Section 5.3 goes into polynomial functions a little bit more in depth than what we've already discussed. So some of it will be some review, and others of it will be, like I said, some more in-depth topics regarding polynomial functions. So we can see here a polynomial function is in the form of f of x or y equals a sub 0 x to the n plus a sub 1 x to the n minus 1, and so forth. And what this is showing is that our powers are declining, because when we're in standard form, we always want to have declining powers. And we can have coefficients out front, and our constant will always be at the end. Now, some other key things is no products of variables, so no x times y's. No variables in the denominator. Remember, that would mean that really it's a negative exponent, and we do not want negative exponents for polynomial functions. Graphs are continuous, so they can be curvy or linear, but they are continuous, no gaps. And unless it's a linear function where we just have a binomial with the power of 1, the graphs will curve and turn, okay? So, standard form of a polynomial, again, written in alphabetical and descending order of powers. Our leading coefficient is the coefficient of the first term of a polynomial in standard form, aka it's the coefficient of the term with the highest degree. Classifying polynomials, these vocab words should not be anything new. When we have one term, we call it a monomial, 2 terms binomial, 3 terms trinomial, and 4 or more terms we just refer to as polynomials. So this chart below has all of the examples here of what a degree would be with the name of that, classifying it, what it would look like in standard form, some examples, and so forth. So if I have a degree of 0, it's going to be a constant, and it would just be a number. F of x equals 7, f of x equals -3, y equals -3. Remember, f of x or y is interchangeable. In this case, the leading coefficient is -3, and so we call that a constant monomial. Our next example, degree of 1, so that's linear, right? Y equals mx plus b form. In this example, the leading coefficient is 2, and I just have one term, so that would be a linear monomial. But remember, I could have linear binomials, right? Y equals 4x minus 3. That would be a linear binomial because there would be 2 terms. Okay, when we have a power of 2, it's a quadratic, which we have already discussed. When we have a power of 3, it's a cubic. A power of 4 is quartic, and we can go higher and higher and higher. Okay, and when we say n degrees, that means the highest degree is n. Again, more examples here of determining what the leading coefficient is. All of these are written in standard form, and then a classification. So usually we classify with 2 vocab words based upon their degree and based upon how many terms. Okay? So let's look at a couple examples together and also have you try some on your own. So the first 2 are just identifying if it's a polynomial function, and if so, write it in standard form. So I'll do the first one with you. We have 5x to the third, x to the negative second, and minus 8. So this is not a polynomial function because of the negative exponent. Okay, you try number 2. And if it is a polynomial function, make sure you write it in standard form. Then we have evaluating. So for evaluating, we have done this before, right? When I say find f of 2, that means plug in 2 for all the x values. I'll let you try that one, but I'll go do example 4 to just let you refresh about that. So if we look at this, it's first saying to evaluate f of 3a minus 5, which means I take 3a minus 5 and I plug it into wherever I see an x. So this would be saying the quantity of 3a minus 5, all squared, minus 3 times 3a minus 5, plus 2. Then it says subtract twice the product of f of a. So the function is x squared minus 3x plus 2, but it's saying multiply that by 2 and plug an a in it. So I'm going to have minus 2 times that quantity of x squared minus 3x plus 2, but really with a's in it. Okay, so now I've plugged everything in that needs to be done, so now I simplify. Remember, this first part means to really FOIL. 3a times 3a is 9a squared, and then I'll have minus 15a, which is minus 30a, and plus 25. Be sure to distribute our negative, so minus 9a plus 15 plus 2. And then make sure to distribute the negative 2. Okay, I'm just going to double check that all those calculations are correct. 9a squared, negative 30a plus 25, minus 9a plus 15, plus 2, minus 2a squared plus 6a minus 4. And I always double check as I'm going because that way you can catch your mistakes a little easier. Now I combine any like terms, so 9a squared and negative 2a squared makes 7a squared. Let's see, negative 30 and negative 9a, negative 39a, plus 6, so that would give me minus 33a. And then we have our constants. 25 plus 15 gives me 40, plus 2 is 42, minus 4 is 38. And there's my evaluated results. Okay, so go back to make sure to do number 3, but much more basic. Okay, here is some new stuff that I want to make sure you pay attention to. So everything is written down in this chart, but you need to make sure you're listening to the explanation. So we're going to be working with the graphs of higher order polynomials. So we've talked about graphing lines and we've talked about graphing parabolas. But what if I want to graph a cubic function, x to the third, or a quartic, x to the fourth, or something to the sixth power? We need to know a little bit more about them. So here are some rules that you want to have memorized. If the degree is even, okay, so the highest degree, so it's 2x to the fourth plus yada, yada, yada. That degree is a 4, right? So if the degree is even, your end behavior, the way the graph ends, so is going to be in the same way, either up, up, or down, down. Now, if the leading coefficient is positive, our graph will be up, up. Think about that with a quadratic, right? When we had x squared and it was positive, the graph opened up, so both ending points were going to positive infinity. When we had a negative, it flipped it. So instead of going up, up, it went down, down. The way we write that is saying that as x goes to negative infinity, so as x goes to negative infinity, right, as I go to the left, it's telling me my y value, or f of x, is actually going up to positive infinity. And then as the x values go towards positive infinity to the right, also the y values are going up. Okay? Whereas in the second one, as the x values went to the left to negative infinity, the y values went down to negative infinity. And as I went to the right to positive infinity with the x's, again, my y values went down. So they both went to negative infinity. Okay? So when you have an even degree, so it's a quadratic, it's a quartic, it's to the sixth power, it's the eighth power, and it's positive out front, we're opening up. End behavior is to positive infinity both ways. And if it's negative, we're opening down, and behavior is down to negative infinity. Now what happens if it's an odd power? If it's an odd power, to the first, to the third, to the fifth, to the seventh. If we're positive, our graph is down, up. So from negative infinity to the first time, and then to positive infinity. If it's odd and negative, it reflects, it flips. So now instead of going down first, it's going up. So as I go to negative infinity, we go up to positive infinity. And as my x values go to the right to positive infinity, the y values go down to negative infinity. So these are rules that you need to memorize, and we will go look at some examples so that you can practice that. Now, the degree of the polynomial is super helpful because it not only tells us about the graph, but it also determines the number of zeros of the polynomial. Okay, remember zeros also means roots, right, or solutions. But it's telling us if the degree is 4, I will have 4 zeros. Okay, now those zeros, though, could be imaginary. They could repeat. So the degree also is going to determine just the maximum number of real zeros. And maximum times the graph will cross the x-axis. Okay, so if my degree is 4, like this example says, then there are 4 zeros or roots. Okay, there is a max, though, of 4 real zeros. So there may only be 3, 2, 1, or 0. Everything could be imaginary, so therefore I have 0 real roots, so therefore I cross the x-axis 0 times. Or maybe I have 2 real roots, and then the other 2, because I know I have 4 altogether, would be imaginary. So please understand there's 4 solutions, 4 roots, but there's only a maximum of 4 real zeros. There could be less. So that also means there is a max of 4 times the graph crosses the x-axis. Again, it could only cross 3 times. It could cross 2, 1, none. Okay? Therefore, the greater the degree, the more complicated the graph can be, right? Because I'll have more zeros and more times I could cross, so then there's more curves. Okay? Again, it's always a smooth curve. Unless we are linear, then it's obviously a line. Okay, so here are some examples of polynomial functions. Our lines we're all clear with, our quadratics, we know our parabolas. Here's an example of a cubic. So this one is starting up and going down, which means I would have a negative out front, but they also could be down and end up. A quartic, we can see here, end behavior, since it's an even degree, the end behaviors are the same, but it's not a parabola anymore, right? Since it's a quartic, I could cross 4 times, and I do in this problem. A quintic is a degree of 5, and notice here I can cross a maximum of 5 times. But because it's an odd degree, that end behavior is opposite. One is down and one is up. So those are just some examples. So let's do some of these together. The first bit is still determining if something is a polynomial function. So what do we think for A? Yes, right? We have all positive powers. There are no variables in my denominator, and there's no products of variables, so this is a polynomial function. Let's jump to D. Is that a polynomial function? Yes, it's all curves, right? It's all curves. There are no breaks, so it's a polynomial function. And it's a polynomial function that has the degree of, how many times do I cross? 1, 2, 3, 4, 5 times, odd and here. So it has a degree of 5 because I crossed 5 times. All right, determine the end behavior of the graph. So I'm going to do A, and you guys make sure to go back to do the other examples we haven't done. So for A, determining the end behavior, what we want to make sure is that we're in standard form. I am. So now I look at that leading term. Okay, so that leading term, you don't have to write this, I'm just doing it for your notes. The leading term is negative, and the degree is 3, which is odd. So when I go to my chart, I'm going to go look at the negative and odd. So if I go up to my chart, negative odd is this row right here. So my end behavior is going to be this, okay? So if we go down, we can see that we will have that as x goes to negative infinity. So we always do the first part as is. As x is going to negative infinity, it's telling us that f of x will also, or sorry, not will also, will go to positive infinity. And as x goes to positive infinity, f of x will go to negative infinity. Okay? And we can go double check that, right? As x goes to negative infinity, f of x to positive infinity. And as x goes to positive infinity, x goes to negative infinity. So what this is saying, just so we're all aware, so this is what your answer would be. This is saying that my end behavior is up and then down. Okay, so you want to use the notation I have circled, but also be able to picture that. That means that the first end is up, then I'm going to have some curves, and the second end is down. Okay, you try B. Make sure we're in standard form, determine that leading term, and then go check out your chart. All right, one more example together. Given the graph, determine whether the leading coefficient is positive, negative, and if the leading degree is even or odd. So I'm going to do B with you. So what this is saying is the end behavior is up, up. Or, as I write that in that fancier notation, it's saying as x goes to negative infinity, right? As I go to the left, what's happening to the graph? It's going up. So f of x is going to positive infinity. And as the graph goes to the right, to positive infinity, the graph is also going up. So now what I'm going to look at is, okay, when my end behavior is the exact same, up, up, or down, down, I know that that's going to be an even degree. And since it's going up, up, right, that means we will have a positive leading term. And we can double check that. Let's go look. Positive, even. Does that give me the end behavior of positive, positive? Let's go look. Positive, even is our first one here. And as we can see, as we go to negative infinity and positive infinity, both of them are going to positive infinity. So we did that correct. Now, a little bonus question is, what could possibly the degree be? So could the degree be 1, 2, 3, 4, 5, 6? Well, we know it has to be even, so that narrows it down to 2, 4, 6, 8, etc. And I see that I cross 1, 2, 3, 4 times, so the degree has to be at least 4. Because remember, the maximum real zeros I can have, but it could have less than that, okay? All right, you go try the rest of these problems, and then we'll check them on in tomorrow.